We begin our examination of interstellar travel not with optimism, but with a rigorous confrontation of physical reality. The consensus among serious physicists and astronomers, specifically those represented by the discourse between Vladimir Surdin, Alexei Semikhatov, and Boris Stern, is that the romanticized notion of manned interstellar spaceflight, as depicted in science fiction, is effectively impossible. We must dismantle the illusion of warping space or finding convenient wormholes and instead look at the universe through the lens of known hard physics. When we ask the question, when will we fly to the stars? The most scientifically accurate answer, particularly regarding biological human crews, approximates to never. Or, to be precise, never within the context of our current biological form and the immutable laws of thermodynamics and general relativity. To understand this prohibition, one must first grasp the scale. The distance between stars is not merely far. It is a chasm of emptiness that defies human intuition. The dimensions of the cosmos are approximately 100,000 times greater than the dimensions of our solar system. To cross the solar system is a feat we have only just begun to manage with robotic probes. To cross the void between the Sun and Proxima Centauri requires a leap in energy and velocity that is not a linear progression from current technology, but an exponential one. We currently possess a standard model of physics. It is robust. It is tested. It describes the universe from the subatomic scale to the galactic scale with high precision. There is a common hope among laypeople that new physics, such as dark energy or quantum gravity, will provide a loophole, a magic button that we can press to bypass the speed of light or negate inertia. However, the analysis of these phenomena suggests they operate on scales irrelevant to human transportation. Dark energy manifests only across cosmological distances, pushing galaxies apart over billions of years. Quantum gravity operates at the Planck scale, far below the subatomic level. There is no intermediate mechanism in the laws of physics that allows a macroscopic object, like a spaceship, to manipulate gravity or spacetime to facilitate travel. We are bound by the conservation of momentum and energy. We are bound by the speed of light. Let us examine the current state of our propulsion technology. Our chemical rockets, the workhorses of orbital insertion and planetary exploration, achieve velocities in the range of 10 to 12 kilometers per second. Even utilizing gravitational assists, stealing momentum from massive bodies like Jupiter, we struggle to exceed 17 kilometers per second. This is the velocity of the Voyager probes. At this speed, a journey to the nearest star would take roughly 70,000 to 80,000 years. This is not a mission. It is an archaeological epoch. To make interstellar travel viable, we must increase our velocity by 2 orders of magnitude. We must reach speeds not of 10 kilometers per second, but of 1,000 kilometers per second, and ideally much more. Even at 1,000 kilometers per second, the journey to Alpha Centauri would take over a millennium. This defines the fundamental disconnect. The speeds required to traverse interstellar distances within a human lifetime approach a significant fraction of the speed of light, yet the energy required to accelerate mass to those speeds increases asymptotically. The next logical step in propulsion evolution is the nuclear engine. We must differentiate here between radioisotope thermoelectric generators, which merely produce electricity, and true nuclear thermal or nuclear electric propulsion. A nuclear thermal rocket utilizes the immense heat generated by nuclear fission to superheat a propellant, such as hydrogen, and expel it at high velocities. This yields a higher specific impulse, a measure of engine efficiency, than chemical rockets. While a chemical rocket is limited by the bond energy of molecules, a nuclear engine is limited by the melting point of its reactor core. However, even assuming we master high-efficiency nuclear propulsion, we run into the tyranny of the rocket equation. To accelerate, you must expel mass. To have mass to expel later in the journey, you must carry it with you at the start, which requires more fuel to accelerate that fuel. This exponential growth in mass limits the maximum velocity of any rocket carrying its own propellant. Furthermore, we must address the most critical, yet often overlooked, limitation of high-power spaceflight: thermodynamics. Specifically, the problem of waste heat. A starship engine capable of relativistic or near-relativistic speeds must process enormous amounts of energy. Even a fusion reactor, often cited as the holy grail of propulsion, is not 100% efficient. If a reactor produces terawatts of power to drive a ship, and is even 99% efficient, the 1% of waste heat represents gigawatts of thermal energy that must be managed. In the vacuum of space, there is no air to carry heat away via convection. You cannot simply open a window. The only mechanism for heat dissipation is radiation, governed by the Stefan-Boltzmann law. This law states that the power radiated from a black body is proportional to the fourth power of its temperature. To dissipate the waste heat of a high-power interstellar engine, a ship would require radiator surfaces of immense surface area, thousands of square kilometers of glowing panels. The structural mass of these radiators would be prohibitive. A proposed solution is the droplet radiator, where streams of hot liquid metal are sprayed out into space to cool down and then collected by a magnetic funnel. However, this system is complex, prone to fluid loss, and mathematically daunting. If the engine cannot cool itself, it melts. If the radiators are too heavy, the ship cannot accelerate. This thermal bottleneck effectively caps the performance of any internal combustion or reactor-based drive, likely limiting nuclear-powered vessels to speeds well below 1% of the speed of light. Therefore, if we are to reach the stars, we must abandon the idea of carrying our fuel and engine with us. We must leave the energy source at home. This leads us to the concept of beam-powered propulsion, specifically the laser sail, as popularized by the Breakthrough Starshot initiative. The physics here relies on radiation pressure. Photons, though massless, carry momentum. When a photon strikes a reflective surface and bounces off, it transfers momentum to that surface. By constructing a sail of ultralight, highly reflective material, and targeting it with a phased array of high-power lasers located on Earth or in orbit, we can accelerate a spacecraft without the burden of onboard propellant. Theoretical calculations suggest that a sail-driven craft could reach 20% of the speed of light. At this velocity, Proxima Centauri is reachable in approximately 20 years. However, the engineering challenges are staggering. To accelerate a payload, even a microchip-sized payload, to such velocities requires a laser array with a power output measured in gigawatts, firing continuously for minutes. The sail must reflect 99.999% of this light. If it absorbs even a fraction of a percent of the laser's energy, the sail will instantly vaporize due to the extreme intensity. Furthermore, we must consider the payload. The Starshot concept proposes sending starships, gram-scale probes. This brings us back to the question of manned flight. A laser sail capable of pushing a human crew vessel, which would mass hundreds of tons, would require energy levels exceeding the total power generation of human civilization. It becomes an engineering absurdity. Thus, we return to the conclusion: biological humans are not going to the stars. The energy cost is too high, the travel times too long, and the physics too unforgiving. But let us assume, for the sake of rigorous argument, that we solve the propulsion issue. We then face the fragility of the human organism. We are evolved for the specific gravity, radiation environment, and atmospheric pressure of Earth. Space is a hostile environment. The most immediate threat in interstellar space is not the cold, but the radiation. The interstellar medium is permeated by galactic cosmic rays. These are not merely photons like X-rays or gamma rays, which can be shielded against with lead or water. These are high-energy particles, protons and atomic nuclei stripped of their electrons, moving at relativistic speeds. When a cosmic ray strikes a human cell, it acts like a microscopic bullet. It shatters DNA strands. It creates cascades of secondary radiation within the body's tissue. On Earth, we are protected by the planet's magnetic field and a thick atmosphere. In low Earth orbit, astronauts are still largely protected by the magnetosphere. In deep space, there is no protection. Shielding a spacecraft against GCRs requires meters of water or lead, adding prohibitive mass to the vessel, which again exacerbates the propulsion problem. A human crew traveling to Mars faces significant cancer risks. A human crew traveling for decades or centuries to another star would likely die of radiation sickness or develop catastrophic cellular damage long before arrival. The concept of cryonics, freezing astronauts, is often invoked as a solution. However, current biological understanding offers no path to reversible cryopreservation of complex organisms. When water in human cells freezes, it expands and forms sharp crystals that rupture cell membranes. Upon thawing, the tissue turns to mush. While some amphibians, like wood frogs, produce natural antifreezes to survive partial freezing, applying this to a warm-blooded human with a high metabolic rate and complex neural architecture is currently science fiction. We cannot pause human metabolism. We can only sustain it or end it. If we cannot send living humans and we cannot freeze them, could we send our progeny? This leads to the concept of the generation ship, a vessel where humans live, reproduce, and die, hoping their distant descendants arrive at the destination. The sociological and psychological stability of such a closed system is dubious. But more importantly, the radiation problem remains unsolved for the fetuses and developing children on board. This forces a paradigm shift in our objectives. If the goal is not tourism, not the physical presence of an astronaut standing on a foreign world, but rather the propagation of life or humanity, we must look to biology and cybernetics. We move from the realm of the macro-astronaut to the micro-payload. The most viable method for interstellar colonization is likely directed panspermia. Instead of sending a fully grown human, we send the building blocks. We could send simpler life forms, bacteria, extremophiles, or perhaps frozen embryos. An embryo is small. It is more resistant to radiation than a developed adult, and it can be shielded more heavily because the total volume to protect is microscopic. However, an embryo requires a womb. It requires gestation. And once born, a human infant requires years of care, education, and socialization. This necessitates the development of an artificial intelligence capability, far beyond our current large language models. We would need an AI nanny, a robotic custodian capable of running an artificial womb, birthing the child, and then raising it. This raises profound ethical and practical questions. Can a machine provide the emotional nurturing required for human sanity? Can a first generation of humans, raised solely by machines on a desolate exoplanet, possess the culture and humanity of their progenitors? It is a scenario that borders on the grotesque, yet it remains more physically plausible than accelerating a 100-ton spaceship to relativistic speeds. Before we dispatch these seeds of humanity, we must know where to send them. We cannot simply launch into the void. We need a target. The search for exoplanets, planets orbiting other stars, has exploded in the last 2 decades. We now know that planets are common. Almost every star has a planetary system. But finding a planet is not enough. We need a habitable one. We look for the Goldilocks zone, where liquid water can exist. We have identified candidates. Proxima Centauri b is the closest, an Earth-mass planet in the habitable zone of a red dwarf. The TRAPPIST-1 system contains multiple Earth-sized planets. However, habitable zone does not mean habitable. Red dwarf stars are volatile. They emit massive stellar flares that could strip the atmosphere of any orbiting planet and sterilize its surface with X-rays. To confirm habitability, we need to study the atmospheres of these planets. This is the next frontier of astronomy. We are looking for biomarkers, chemical imbalances in the atmosphere that suggest biological activity. Oxygen is a prime candidate. Oxygen is a highly reactive element. It wants to bind with rocks and carbon. If we see a planet with a stable, high percentage of oxygen, something must be constantly replenishing it. On Earth, that something is photosynthesis. Methane is another marker. If we find oxygen and methane together, it is a strong signature of life, as they react with each other and shouldn't coexist for long periods without biological sources. We must also look for the red edge, the specific reflective signature of chlorophyll or its extraterrestrial equivalent. Plants reflect infrared light to avoid overheating. A telescope powerful enough to resolve the spectrum of an exoplanet could theoretically detect this vegetation signature. This search for life brings us to the Fermi paradox. If interstellar travel is possible via these slow, robotic, panspermic methods, why hasn't it happened to us? The galaxy is billions of years old. Even at slow propulsion speeds of 1,000 kilometers per second, a civilization could colonize the entire galaxy in a few 100 million years, a blink of an eye in cosmic time. Yet, we see no von Neumann probes eating our asteroid belt. We see no alien megastructures. We detect no radio signals. This silence suggests a filter. Perhaps life is rare. Perhaps intelligence is rare. Or perhaps the technological hurdle of interstellar travel is simply too high, and civilizations turn inward, living in virtual realities or essentially dying out before they can muster the titanic energy required to cross the abyss. Or there is the biological barrier. As we discussed, humans are fragile. Perhaps advanced civilizations realize that biological bodies are merely a substrate for intelligence, and they transition to post-biological forms, uploading consciousness into machines. A machine does not need a habitable planet. It does not need water or an atmosphere. It can reside in the cold vacuum, powered by starlight. If such civilizations exist, they have no need to terraform planets or interact with biological entities like us. They may be everywhere, yet invisible to our search for biology. Let us return to the mechanics of the Starshot project. as it is the only engineering project currently receiving serious theoretical funding that addresses the speed problem. The proposed nano-craft would weigh perhaps 1 gram. It would contain cameras, communication equipment, and navigation sensors. It would be tethered to a light sail, a few meters wide and only a few hundred atoms thick. The launch phase is the most critical. The ground-based laser array fires a pulse of energy equivalent to the output of many nuclear power plants, concentrated onto this fragile sail for a few minutes. The acceleration is brutal, tens of thousands of g-forces. The electronics must survive this crushing force. The sail must not buckle or tear. Once the laser turns off, the craft coasts. It travels through the silence for 20 years. During this cruise, it must survive the erosion of the interstellar medium. Even singular atoms of hydrogen striking the craft at 20% the speed of light act like cosmic sandblasting. Dust grains could be catastrophic. Upon arrival at Proxima Centauri, the flyby happens in an instant. The craft is moving so fast it cannot stop. It has no engine to brake. It screams past the planet in minutes, snapping photos and gathering data. Then comes the hardest part, sending the data back. The craft has a tiny transmitter with the power of a laser pointer. It must aim this beam back at Earth, 4 light-years away, with absolute precision. On Earth, we must have a receiver, likely the same laser array used for launch, now acting as a telescope, waiting to catch this faint whisper of data 4 years after it was sent. The signal will be incredibly weak, requiring advanced algorithms to filter it from the background noise of the universe. This robotic reconnaissance is the realistic future of interstellar exploration. It is a future of data, not footprints. It is a future of remote sensing, not colonization. But let us briefly entertain the far future possibility of terraforming and colonization, assuming we solve the transport issue with suspended animation or generation ships. To plant life on a dead world is a task of geological magnitude. We would need to create an atmosphere. If the planet has no magnetic field, the solar wind will strip away any atmosphere we create. We might need to construct artificial magnetic shields, massive superconducting rings in orbit, to deflect the stellar radiation. We would then introduce cyanobacteria to produce oxygen. We would need to import water, perhaps by redirecting comets to impact the surface, a violent and chaotic process. This engineering of a biosphere takes thousands of years. It is a project that requires a stability of purpose that human civilization has never demonstrated. We struggle to plan for the next century. Terraforming requires planning for the next millennium. There is also the question of genetic adaptation. Rather than changing the planet to suit us, we might change ourselves to suit the planet. If a planet has higher gravity, we might engineer humans with denser bones and stronger hearts. If the oxygen content is low, we might modify our hemoglobin. This leads to the speciation of humanity. The humans who colonize the stars would eventually cease to be Homo sapiens. They would become a distinct species, separated from Earth not just by distance but by biology. The discussion of interstellar travel often circles back to the motivation. Why do it? The Earth is perfect for us because we evolved here. No other planet will ever be as perfect a fit. The argument for a backup drive for humanity, in case of asteroid impact or nuclear war, is valid, but the cost of establishing that backup is currently higher than the cost of safeguarding our primary drive, Earth. However, scientific curiosity is a potent force. The desire to know if we are alone is overwhelming. This is why we will continue to refine our telescopes. We will build the extremely large telescope and future space-based interferometers to resolve the disks of exoplanets. We will analyze the spectra of distant atmospheres with increasing precision. We will listen for radio signals. And we may, eventually, launch the Starshot probes. Not to colonize, but to witness, to see a red dwarf sun rise over an alien horizon, even if only through the digital eye of a gram-scale robot, is a goal worthy of the immense physics and engineering challenges involved. In summary, the reality of interstellar travel is defined by constraints. The constraint of the speed of light, which makes communication and travel agonizingly slow. The constraint of the rocket equation, which makes carrying fuel impractical. The constraint of thermodynamics, which demands massive radiators for any high-power engine. And the constraint of biology, which makes the human body a poor candidate for spaceflight. We are confined to our solar system for the foreseeable future. Our expansion will be robotic. Our eyes will reach the stars long before our feet do. The laws of physics do not strictly forbid interstellar travel, but they enforce a toll so high that it renders the space opera version of the future impossible. We will not have warp drives. We will not have Millennium Falcons. We will have massive laser arrays, delicate solar sails, and patience. We will have nuclear tugs moving slowly between the planets of our own sun. And we will have the quiet, rigorous work of astronomers analyzing the faint light from distant worlds, looking for the telltale chemical fingerprint that says, "We are not alone." This is the sober, scientific perspective on our place in the galaxy. We are islanders on a distinct shore, looking across a vast, dark ocean. We can send messages in bottles. We can look through spyglasses. But building a ship to cross that ocean requires resources and technologies that we are only just beginning to imagine, and which may forever remain beyond the reach of biological entities. The stars are not our destination. They are our study. And that, for a scientist, is enough.